Okay, let's try this again. I'm outside right now because it's pretty loud in my house. First, I want to apologize for not making the video earlier in the week when I had said I was going to make it. The internet at my house went out, so I ended up just not being able to upload anything. So I'm trying to make it now, and of course, dinner's going on in there. But we're going to get it done. I really wanted to talk about the example on slide 24 of your slideshow. And as I'm recording this, I do want you all to look over my shoulder. You see the moon right there and Venus right there. So that's pretty cool for those of you who are interested in astronomy. But anyway, for what we're focusing on right now, we're talking about energy. And the question that we're looking at says that you throw a 0.4 kilogram stone straight up into the air, and it's initially at rest. Your hand exerts a force of 150 newtons upwards on the stone through a distance of 0.75 meters. And the question is, how high does the rock rise? So in order to answer this question, we need to know at least two different things. One, remember, the law of conservation of energy says that the sum of energy should be the same before and after the rock finishes its motion. And of course, know also that work put into a system will change the amount of energy, and that's related to the work energy theorem. So we're going to use those two truths to find out this question. First, we're going to want to know how much work is done to the rock by your hand. So in order to find the amount of work that is done to the rock by your hand, remember that work, W, equals force times change in position. F, change in position. The force is 150 newtons, and the distance is 0.75 meters. So that means that the total work done on the rock by your hand is 112.5 joules. 112.5 joules. Now, if we think about how work relates to energy, since the rock had no energy before, because it was initially at rest, right? Putting that work on it will give it a certain amount of energy, and the amount of energy that it's given is that 112.5 joules. So once the rock leaves your hand, it will have 112.5 joules on it. So the rest of the time the rock is flying up and falling back down, it will have that same 112.5 joules worth of energy. That's super important. Okay, now let's think about the rock as it travels through its path. It's moving upward at some speed. We don't know what speed it's moving up at. It's moving up at some speed. We know that the sum of energy it has is going to be its potential energy plus its kinetic energy. Its potential energy plus its kinetic energy. Now, we don't know how fast it's going as it's flying up, and we don't know how far away from your hand it is, so we don't know how high it is. So we can't really find one of those two things specifically, but we know that the two added together, kinetic energy, Ke, plus potential energy, U, is equal to that 112.5 joules. However, let's think about the rock at the top of its path. At the top of its path, remember, the rock's going to stop moving for an instant before it starts falling back down, right? We learned this earlier in kinematics section. So, at the top of its path, the rock has a velocity of 0. Well, kinetic energy is 1/2 mv squared, and if the v equals 0, then that means at the top of its path, it should have no kinetic energy. Well, this is super beneficial to us, since the sum of energy is the kinetic energy plus the potential, and it's constant. What this means is that at the top of its path, it's going to have no kinetic energy, only potential. And since the total is constant, the potential energy is going to equal the total energy at the top of its path. You probably noticed this from working with the PhET tutorial. So that means that at the top of its path, the total energy equals the potential energy, which equals that 112.5 joules. Wonderful. since the potential energy also equals mgh, that's mass times the acceleration due to Earth's gravity times the height, we can find the height. So we'll take the potential energy, which we know to be 112.5 joules at the top of its path, and we will divide that by the mass, 0.4 kilograms, and the acceleration due to Earth's gravity, 9.8 meters per second squared. Once we take 112.5 divided by 0.4 times 9.8, right, we get 28.7 meters for our height. So it says that our height should be 28.7 meters. But I want you to think about it for a second. 28.7 meters above what? And remember, that's going to be 28.7 meters above where it left your hand. It's 28.7 meters above where it left your hand, because that's what we define it as, right? We define the point at which it got its total energy, 112.5 joules, as that's where we're starting, right? And that's where it leaves our hand. So that's going to be our zero height, where it leaves your hand. And so it's going to end up 28.7 meters above where you let it out of your hand. And so hopefully that helps you with that question. Of course, I'm going to have to make a lot more videos tomorrow to catch up for the weekend that I couldn't do anything. But hopefully this helps you with this one. I'll start working more through the homework ones. I actually have all the homework problems worked out, so I'm going to see if I can maybe scan those in somehow. My scanner broke, but I'll figure it out, right? So, of course, email me with questions, and I hope this helped a little bit. Thank you all, and have a safe evening.